Welcome to the webinar Advanced Plastics Applications for Recovered Carbon Black. My name is Martin von Wolfersdorf. I'm a chemical engineer. I worked 14 years in titanium dioxide, 2 years in color master batch with Americam Europe, 2 years in carbon black with Cabot. I have a global consultancy and I help companies sell their chemicals and materials. And I have a special passion for recycled materials like recovered carbon black.
Yay!
These are some of my reference customers. Many customers are recovered carbon black companies, tire companies, or plastics companies, master batch companies like Compuestos, or packaging companies like Coveris. A little bit about the basics, the free tire-to-tire recycling processes. We are looking today at a product that is made from pyrolysis. There are other methods, of course, powder recycling and devulcanization. What are the basics? So the mass flows of the pyrolysis, the input is end-of-life tires, and that could be car tires, that could be truck bus tires, that could be OTR tires. Typically, we get about 33 to 40% raw recovered carbon black. The pyrolysis process is a thermal process in the absence of oxygen. So we're heating between 400 and 1000 degrees Celsius. We get about 10% gas. We get about 45% oil. We get the recovered carbon black, about 33%. We get a 12% steel. And it's very important to know that recovered carbon black is not a pure substance. It's a mixture of materials. So we have the recovered carbon blacks. We have the inorganics. That could be the silica from the tread. That could also be crystalline silica from the sand in the tires. We should only have zinc sulfate and not zinc oxide. Zinc oxide is a accelerator of the vulcanization package in the tires, which shouldn't be in the final product. And process depending, we have volatile hydrocarbons and we have fresh carbon coming from polymer carbonization. I'm often talking about quality categories, and I'm bringing up this table again about the quality categories. Quality rCB. 1 is the full specification compliance. And this one, which is for plastics and coloring applications, is the toughest specification for recovered carbon black. rCB2 would be a quality category where recovered carbon black has 1 or 2 properties deficient, and rCB3 is untreated recovered carbon black. The most important property for recovered carbon black is consistency. We get back to that in a moment. How do we measure consistency? With a TGA? With the ISO method 9924, or with the ASTM method, rCB bulk composition test method. This is a method that is still in work. It hasn't been published yet. And at the moment, I would recommend we don't need to specify a minimum for carbon, ash, and char. In general. However, we get back to the carbon content and the ash content in a moment, because for coloring applications, only the carbon content is coloring black, and the ash actually would be a white pigment. We need very low volatiles. I'm recommending 1.5% volatiles maximum. That's total volatiles, moisture, and organics. We want a toluene transmittance of at least 80%. We want a benzoapirin content of less than 1 ppm, and we want the EU pH 8 group of 8 pH to be less than 8 ppm. This will enable us to be much more performing than furnace carbon black. In fact, to be as performing as the low pH carbon black range. And that is significant value creation. That could mean that the price is around double of the price of normal carbon black. The milling, I would say certainly D99 below 10 micron. I'm indicating here black bear carbon, of whom we will talk in a moment, have a D98 of less than 3 micron. And you will understand in a moment. This is all about dispersion. Pellet hardness is very important as well because we need to disperse the pellets in the first place. And what I'm recommending is an average pellet hardness of 60 gram maximum and a maximum pellet hardness of 80 gram maximum. If we don't disperse the pellets and if we don't disperse the agglomerates, which are within the pellets, we cannot expect color performance. What about quality control? We talked about consistency. There are very few data points on consistency. I want to introduce you Boulder Industries, who are the first company that actually published some data on the consistency. As you can see in the chart, they have been measuring certain properties of the recovered carbon black in their testing schedule. I'm showing the raw carbon inorganic content, so this is the ash content, and they have a specification of ash content to be maximum 20%. And here you see all the data points. Of course, there is some data points which are out of the specification. Also, Boulder have highlighted they've been getting deliveries, probably including European passenger car tires with a higher ash content in the red area. What also is interesting is the testing scheme, the schedule for testing. For example, on the raw carbon inorganic content, every 2 hours, some tests as needed. This kind of schedule is very important for the consistency. Color is all about consistency. You might argue even applications in wellbore reinforcing are about consistency. And consistency is the number one quality property of recovered carbon black. And it's a major weakness as well. What I really like to see is Boulder indicate moving forward. They indicate moving to a process capability Six Sigma method with the CPK value. So that is really where I see the future of quality control for recovered carbon black. And this data has been taken from the industry white paper from Boulder Industries, How We Make Boulder Black Consistent. Very good paper and very good initiative. And I'd like to see all the other manufacturers of recovered carbon black to do the same, because this will significantly increase the image of recovered carbon black and the reliability of recovered carbon black. Now, in terms of improvements for coloring, this is a slide I've already presented also on the first webinar on rCB in the master batch. It is very important to understand what is important for coloring. And the first is the carbon content, reducing the ash content, increasing the carbon content. And there's various levels. The first level is just segregating the type of the tire. Second level is the TGA analysis. The third level is the XRF analysis as done by Black by Carbon. I have a full slide on that just after that slide. Of course, if you have an ash content, you could also do some post-treatment like acid-base methods. However, it's very expensive, between 400 and 2,000 euros per ton. There's a new company called rCB Nanotechnologies that do hydrothermal ash leaching that promises to do the same for 200 euros. I would say if you can combine the feedstock selection by XRF analysis, maybe you don't have to take the ash out, or you combine XRF analysis of the feedstock together with hydrothermal ash leaching. That would be fantastic. Then it also plays a role, as you might know, in the tires. There are different carbon blacks in different sections of the tire. And the carbon blacks we want are certainly carbon blacks that are small microparticles. And with small microparticles, I would say at least less than 51, like in the chart on the left, on the right-hand side. It would be best to have a microparticle size of 25 to 20 nanometers. And on that chart, you can see the effect of the microparticle size on the jetness, My, and you can also see the L value. The L value is an estimated, calculated value. That data comes from Orion Engineered Carbons. Very good white paper, black, the fine details. That was also mentioned in the previous webinar. Now, we're talking about dispersion. How can we get dispersion control? We need to minimize the agglomerate size. And so definitely black bicarbon milling below 3 microns. This is helping in the dispersion in plastics. Feedstock control. We talked about black bicarbon feedstock control. This is how it looks like. Black Bear has a patent, worldwide patent filed in 2017. It's called a method for sorting tires, which is an online XRF analysis to control the silica content to 1% precision in the range of below 2% to 25%. And they are mentioning a specific device from Baltic Scientific, the CON X03M. And this is an online XRF device which is measuring silica and the whole contents of the tire just by the tire passing. And the tire only needs to be at 2 millimeter distance to the sensor. So I think from what I understood from Black Bear, this obviously is not the picture from black bicarbon, but this is another application on the conveyor band. But you could imagine the tire to be on that conveyor band and the measuring device not from the top overhead, but from the side. And this is pretty much what black bicarbon has installed. And then as a function of the measurement of each and every tire, the tire is going to a certain grouping, and thereby black bicarbon can ensure that they can have specific runs of various types of tires with various silica content. We'll get back to that in an application slide a little bit later on. This is also an old slide from the last webinar, but it's absolutely key, so I'm showing it here again. What we want in black coloring, the ultimate would be the jet black. There's different blacks, and perhaps the black we can compete the most with the rCB master batch is the signal black. And in the last webinar, I've shown there's some optimization we can do. As mentioned, when we select truck tread, not the whole tire, but just the tread containing ASTM 100 and 200, then we have 94% carbon black. We mill below 10 micron. Here, I would even say below 3 micron for sure. We get much less reflectance, more absorbance, and that's what we need for the jetness. I've been often asked about the plastic labs, so the one plastic lab I've previously worked with for my client Alpha Carbon was Aimplast, where we did filter pressure testing, we did opacity testing, we did also color testing, and that was good work. The other lab may be a little bit more expensive, like everything German is a little bit more expensive, is the SKZ in Würzburg, but essentially they have the same competencies as the Aimplast lab. Can compound the master batch, then they can let down the master batch to final applications like films or plaquettes of color. So let's go to advanced plastics applications. And the one thing I'm very deeply impressed about the work from black bicarbon. This is an example of black bicarbon, recovered carbon black in polypropylene. Now, polypropylene is still a polyolefinic resin, but it goes in the application range of engineering plastics. I put the picture of an automotive mid-console in there. The automotive mid-console, that could be either polypropylene or that could be a nylon. The mid-console I'm showing in that picture is actually piano black, which is super deep black and very glossy. That is perhaps the highest performance. Perhaps recovered carbon black wouldn't perfectly fit for the piano black, but rather for the dark grays. But here are some real data from black bicarbon, and we're comparing against two P-type blacks. What are P-type blacks? So P-type blacks are pure carbon blacks, And in terms of the specific surface area and the structure, they come very close to an ASTM N100 or N200 range. So they have a fairly high surface area, high structure as well. And they are pure, meaning they're low pH value. And this is precisely what rCB can compete with. And so here are two different sets of values. We have the full tone and we have the tint tone. The full tone is just a black, and we're measuring the black. And then we measure the jetness, the MY. And the tint tone is actually when we mix a black color with a white color, and we go into the grays, and we're looking at how much the master batch with the recovered carbon black is darkening up the white master batch. So is it rather a dark gray or is it a light gray? Several observations which I noted in green next to the table. So first, in the full tone, we look at the LAB of the C-lab. The L is the lightness, the A and the B are the color axes, and we are specifically interested in a blue undertone black, because the blue black is the most intense black. So we look at the B star. And what can be said about the comparison of Neptune 70? Neptune 70 is the top of the range recovered carbon black from Black Bear. If we do a one-to-one replacement, we don't get quite the color performance yet of the P-type carbon blacks. We get close to it. Also, what we note is if you put in more of the recovered carbon black, we don't get improvement, but we get pretty close to the L. Actually, the L slightly being lower than the P-type blacks. The B being bluer, so this is in full tone. It's looking really good. In terms of the jetness, we are in between the two P-types from Cabot and Orion Engineered Carbons, Printix P and the Black Pearls P100. So looking pretty good in the full tone. Now in the tint, in order to get the low L value for the tint, we need to add 40% more recovered carbon black. That might be a cost factor, but there's a nice story from Ad van Oorschot from Black Bear. If you add 40% more recovered carbon black, your dosing precision actually increases. And when your dosing precision increases, then the amount of scrap material gets reduced. So this is actually a plus. You can control the dosing much better when you add more material, and you get the desired color much easier. So here for the tint tone in the gray, we need to put in 40% more recovered carbon black, whereas in the full tone, a one-to-one replacement was sufficient. And keep in mind the Neptune 70 is containing ASTM 100 and 200. This is from TruckJet. And what's also interesting when we look at the gloss values, we have actually a higher gloss than the two P-types, and that indicates the good dispersion. So dispersion is as important for the recovered carbon black as it is for the normal carbon black. Normal carbon black typically is not milled or only hammer milled. The typical agglomerate size could be easily 30 microns. If you mill the recovered carbon black to 3 micron, which is 10-fold smaller, we can expect better dispersion. So the more we mill, the more we can expect gloss, the more we have a dispersed recovered carbon black in the plastics. So that's a nice example of recovered carbon black in polypropylene. The next application example is UV light protection. And I'm showing you the spectrum between X-ray and infrared. You can see the visible light between the red and the dark purple. Then we have 3 different spectra of UV, the A, B, and C. You can see the wavelengths get smaller and smaller. And we have As a function of different resins, HDPE, PVC, polypropylene, here the example is isotactic polypropylene, or nylon 6 polyamide, we have different absorbance of the polymers. Now, if you want to protect, for example, a agricultural film, like a bale wrap as pictured in the picture on the top right, we would add typically ASTM 200 or 300 carbon blacks to it. Of course, they have different names. There's a redundancy between the rubber grades and some of the plastic grades. But what we really want for the UV light protection, we want microparticles between 22 and 25 nanometers. So we have to be ASTM 200, the small particle size 300, or even go for an ASTM N100. Addition rate is about 2%, 3% is the maximum. The more we put does not transfer into better protection. And the application is pipe, polyolefin agricultural film, pond linings, automotive parts, and exterior cable jacketing. One word of caution, the liability in that application is very, very high, and the complaints are very costly. For example, I purchased master batches for the packaging company Coveris, and that was pretty much one of the applications was pretty much the bale wrap, like shown in the picture. The black bale wrap seems to be very popular in the UK. Here in continental Europe, we like the white bale wrap, and there the UV protection is more by reflection with titanium dioxide. Also, you might see when you look on the fields, I think by now all the harvest is a long time done, but just after the harvest, you might have seen bales in the fields. Very often blue is a color as well, but green is very popular. There's a light green and a dark green for bale wrapping. There have been specialty films, even in pink for supporting cancer research. But here we're looking at the black agricultural film. The problem is there's only 2 to 3% carbon black in the final application. The film is a multi-layer film. So very often you have a white layer, you have a black layer. You have up to 7 layers, actually. And sometimes not only the UV light protection is important, but also the color. I had, at my time with Corvis, I had a complaint, which was not so much about the UV protection performance, but about the color durability. That was a green bale wrap, and the color changed, patchy, and there was absolutely no scheme to it. It was very difficult to find out what happened. But the volumes produced of these films are enormous. And very quickly, you are in complaint costs between 2 million and 20 million euros. So I would probably say, although we could probably engineer a recovered carbon black that is fit for purpose, we would do the ash reduction, we would select the truck tread so that we have the correct carbon blacks. Probably we could do something, we could engineer something, but just the liability of these specialty applications is very, very high. And I wonder whether standard rubber applications would be much easier to cover. So this probably, although I would say it's technically possible for recovered carbon black to offer UV light protection, if we do our processing right, I would probably not recommend targeting that market. Now, conductive plastics are another possibility, and we need a whole lot of post-treatment. So first of all, what do we mean when we talk about conductive applications? Generally, the electrical resistance R needs to be below 104 ohm meters. So let's look at some basics of the units. The conductivity is measured in Siemens per meter and is inverse proportionate to the resistivity, which is ohm meter. The electric resistance R is with the resistivity is multiplied by the surface divided by the thickness of the layer, and then we get the resistivity. What kind of carbon blacks do we have that are considered conductive? Actually, in the carbon black spectrum on the chart on the left-hand bottom, we see the specific surface area up to 250 meters square per gram. The conductive grades, they go much beyond that, as you can see in the table on the top right. So conductive carbon blacks are considered to have a BET specific surface area of around 120 meters per gram. They typically have an OEM structure of 100 milliliter per gram. Then if you get into superconductive, that's already at the end of the chart on the left-hand side. We have 250 meters square per gram and 180 milliliter per gram structure, all absorption number. But then we have two more classes. We have the extra conductive and the ultra conductive. Now, these are carbon blacks that are pretty much like activated carbon with very, very high specific surface areas, very, very high structure. If we go beyond the ultra conductive, we would get into nanomaterials like carbon nanotubes, or which is the ultimate conductive material, single wall carbon nanotubes. These are tubes pretty much like hoses of one atom layer of carbon, and they typically have a diameter of 5 nanometers and a length of 100 nanometers. And as you can imagine, they have a super high specific surface area per weight. What can we achieve with recovered carbon black? So let's go back to the carbon black spectrum chart on the left-hand bottom side. In gray, we have some ASTM carbon blacks. You can see on the left-hand bottom the N772, 660, the 550, the N330. You can see one black dot, which is the rCB. That's standard rCB. Now we can go two routes. We can go increase the structure, and one way of doing this is actually leaching the ash. Because if we take out the ash, we will get recovered carbon black that appears to have a higher structure. Of course, we're not changing the microparticle size. We cannot change the composition of the carbon blacks we have recovered from the tire. But it will look like as the structure is increased if you have ash leached the recovered carbon black. And that gets us into an area where we have conductive carbon blacks like Conductix, Ultra, and Sacco. Not quite the Super P. Super P is carbon black that is used for battery electrode applications. So that's a super high structure, but also super high surface area carbon black. We can go also the other way. We can activate the recovered carbon black. And we have three examples of activated recovered carbon black, 1, 2, and 3. And we can see that with the activation, we can get even over 200 meters square per gram without changing too much the structure. Of course, the ideal case would be that we increase the surface area and we can increase the structure. Maybe if we can combine the activation with ash leaching, we can go both ways. Here we get into an area of carbon blacks that could be, for example, the Vulcan XC72. That's like the entry-level conductive carbon black from Cabot. It sells at higher prices as 3,000-4,000. And so you see the value of conductive carbon black. And I find the activated recovered carbon black number 2 is already pretty close to Vulcan XC72 in terms of surface area. Of course, the electrical performance depends also on the carbon content. And if you only activate, we don't get the full performance. Another conductive carbon black is the Printex L, which is the red triangle. Now, interestingly, we have received data from G3C Technologies, a Georgian US company that has a technology for activation, also for ash leaching, but predominantly for activation. And we have some application data in polyethylene. And here we compare with the conductive carbon black Sterling C from Cabot. And so just looking at the resistivity, we see that the recovered carbon black is pretty much on par as their sterling C conductive carbon black. Now, this is in a system of 33% carbon black and 66% polyethylene. If we're using a little bit less carbon black, you see the values on the right-hand side, and there's two variants of activated recovered carbon black. This is showing the potential for recovered carbon black in conductive applications. And the applications, there's of course the pure conductive applications. Applications could be, for example, in packaging, like the film shown in the top right corner. Anti-static packaging of electronics, for example, is the typical entry-level application for conductive carbon blacks.